Okay guys, welcome to Projectile Motion. Today we're going to go through the vector nation of projectiles, over here somewhere, resolution and components, also over here somewhere, the time of flight, max height and range calculations. There's a few variations on that same theme, and bearing in mind there's three main types of questions that you can be asked in this section. Sorry, three main types of projectiles. I'll cross that out at some stage maybe. The three equations that we're going to be using should look familiar from last year, hopefully. They're on the equation sheet that you've been given. The final velocity is equal to the initial plus some acceleration over a length of time. So here we're looking at projectiles. They are objects, that are under the influence of gravity. Gravity being straight down, not upwards, not sideways. And we've got the distance covered, so vertical distance covered is v naught t plus half at squared. Here we can put in time of flight, or the time at any point throughout the flight. V squared is v naught squared plus 2as. Another sort of smushing together of these two. So depending on what we know about the question, we can answer all three types using just these things here. Alright, so the vector nature of projectiles is really important to understand because we have a horizontal component, we have a vertical component. And these two components are completely perpendicular to each other, and they're mutually perpendicular, so they're always the same, always perpendicular to each other, but they do not influence each other at all. So if you increase the horizontal one, it won't do anything to the vertical one. They're independent of each other. If we're looking at a very specific projectile path, we can, launch at an angle theta at a speed of v. If we're increasing the angle theta, we will increase this one and decrease this one, and so on and so on. So I guess they do loosely relate to each other, but when we're working out time of flight, max height and the range, we separate these two. So we need to keep in mind that if we're looking at range, this is a horizontal distance, so a horizontal speed, horizontal acceleration, which cancels out unless there's drag. In this case here, if we're talking about vertical height, so the maximum height that it reaches, we're looking at a horizontal vertical velocity. We're looking at a vertical velocity, can't have a horizontal one, and we're looking at the vertical acceleration, which is actually just gravity. Alright, so these two are separate ideas. Alright, and we have to keep them separate. One of the biggest challenges you'll find in this section is to keep these two things separate, and also separate from this thing here. The number one step I will get you guys to do is to split them. So you split V, so this V here, the overall launch velocity, overall launch speed with its angle is the overall launch velocity, into the vertical part and the horizontal part. Split into VH and VV. We use V sine theta, sine is the vertical, cosine is the horizontal here. We use those two formulas to split this into these two. So we're using what we know about the question to split it into its horizontal and vertical components. That way we're less likely to get confused further along. If we're trying to do this resolution into components, we need to know some stuff. So we need to know that, or that. We need to know this and this. We need to know the launch speed, the launch angle, in order to find this or to find this. However, if we're told theta and we're told the horizontal component, we've got this relationship between them, so we can actually resolve back to the initial one, and then we can find out this one as well. Alright, so there's a lot of stuff we can do. First step though, split into horizontal and vertical components. Now, I'm going to jump to this part here where we're talking about three types of questions. So one type of question, and we'll go yellow. One type of question is where you get a normal projectile path that looks like this. So this is someone throwing a basketball, kicking a footy, hitting a golf ball without the influence of wind drag. Next example is where we are projecting a projectile, rock off a cliff type scenario, okay? And the third one is when we're throwing something straight up in the air and it comes straight back down again. In all of these scenarios, we can actually find the time of flight, the max height and the range using the information that we're given. Now, hopefully you've spotted that, in this case here, if we're throwing something horizontally, throwing a rock off a cliff horizontally, we have no initial vertical velocity. And in this case here, where we're throwing something up in the air, we have no horizontal velocity whatsoever. Okay, so in this case here, we're these two cases, we're basically inferring these two values. In this case here, we've got this one where we can actually calculate these two values. From that, we can use these equations over here to rearrange and get time of flight. So let's do that now. Let's look at the time of flight for this case and this case. Okay, so if we look at those two things, we're going to know the vertical and we're going to know the horizontal, and we're also going to know that acceleration is only vertical and it's only due to gravity. So we can start off with v equals v naught plus at. Now we're trying to solve for t, so we need to get it on its own. And we remember bod mass, bed mass, those things, we're going backwards, so we're doing SAMDEB or SAMBED or something or other. We're going to go backwards so we rearrange this thing to get t on its own. And if we do that, take v naught from both sides, divide through by a, we end up with t is v take v naught over the acceleration due to gravity. Now this is kind of useful. If we want the entire time of flight, we put in what the vertical is going to be at the end and what it was at the start, gravity, and we'll find out the whole time of flight. If we want to know what the where the maximum height occurred though, that's up here. So we don't want the whole time of flight, we only want half of it, or we can substitute 0 in for the vertical velocity, because remember at the top it's going to be nothing, and this is our original vertical, and this is our acceleration due to gravity, which is straight down. So this will actually give us whatever we want. So wherever we want along the flight path, we want here, we can plug in 0 for the vertical. If we want here, we put in the opposite of what it launched up at. So if it launched up at 12, it's going to come back down at 12. Remember, if we get rid of gravity, get rid of wind drag and stuff. We also need this to find the range. So we can take this number and this one here, and we can stick it over here and over here, and that will actually give us our maximum height. But we can also take that number and take that number for the entire time of flight, plug it over here, and we can use that to calculate our range. So in that case, we're going to be left with s, which is the distance, is v naught t. This v naught is now our horizontal range, so we're on a horizontal velocity, and this is going to be a horizontal acceleration, which doesn't exist. So our vh is constant, no forces when there's no wind drag. Alright, so horizontal velocity is going to be constant because there's no forces. With no forces, no accelerations, and so on. The only acceleration these things will experience is vertical, up and down. So we can plug it in here and we end up with just this thing. What you'll see, range is VH, specifically the horizontal, times by time of flight. And that'll tell you how far this projectile is going to go. With scenario, so that's for this one here and this one here. Hopefully in this one here you can see that horizontal velocity is 0, so 0 times anything is nothing, so no range here. We can calculate a range here. With this one we need a different way to get to time of flight, and the way you'll get that is rearranging this equation. So we'll know what that is. We'll know the height off the cliff. We'll be told how high the cliff is, or how high the plane was above the ocean when they threw the life raft out, or whatever it was. So we'll know this. The initial vertical here will be 0 because we're throwing it horizontally. We're not going to throw it downwards, we're not going to throw it upwards, because that becomes a complex mashup of this question and this question. We don't want to do that to you just yet. But what we can do is rearrange that thing. S is v naught t plus half a t squared, and we're looking for time here, no initial vertical velocity, so s is half a t squared. Rearranging for t is 2s on a, that's t squared, so we need to square root it. Now we can find out that time of flight, and exactly the same deal, plug that into here for the range and plug it into here for the final vertical velocity. Okay, so that's a way to find out the maximum height, is this one, but we're looking at vertical velocity, so the vertical initial vertical component, final vertical component. With the range, we're looking at the horizontal version of that, so it's probably best if you actually write range equals blah blah blah, so you can stick those things together. The key parts to get out of this little section is that horizontal velocity is constant. and the only change is because of gravity. So here's our projectile path. If I'm going to draw the acceleration due to gravity in blue, the acceleration due to gravity in blue is going to be constant all the way through its path. If I was to draw the vertical velocity in white, at the start we have, you know, a bit of vertical velocity. Here we've still got a little bit left because it hasn't quite reached the top. If I was to do it at the top, there would be no vertical velocity. Over here we've actually got some vertical velocity on the way back down. Direction is important, and we're going to go green because there's not a lot of green up here yet. This is going to be our horizontal, and our horizontal without any forces, remember it's constant because there's no forces because we're saying that there's no air drag, is going to be constant throughout the flight. Alright, this is a reasonably brief intro into this sort of projectile stuff. There is more in the Essentials workbook. There is more in the notes and things that I've handed you and we've worked through before. But this will actually give you the basis to be able to cover most of the stuff in this initial section of the course in, you know, a reasonable amount of detail, relatively comfortably. Okay. Thanks guys, and I'll flick to the next one in a sec.